Okay, so today we're going to start our unit on exponential and logarithmic functions. And the reason I'm showing you this page, first of all, is because this warm-up kind of goes back to what we talked about when we introduced polynomial functions, right? So back in the day, we looked at a table of data and we said, is it linear? And in order to figure out if it was linear, we would find what we would call the first differences. So we'd say, okay, well, 120 to 60, as long as this year is going up by the same amount, and it looks like it's going up by 1 every time. So the difference here would be 60, and the difference for the next set would be 120. And because the differences were not the same, we do the next one would be 240. We would say, nope, it's not linear because the first differences are not the same. And then we would check to see whether or not something was quadratic. We would say, okay, well, why don't we check the second differences? All right, well, the difference here is 60, and the difference in the next one is 120. And if we had gone further, the following difference would be 240. So is it quadratic? Nope. Those second differences are also not the same. But when the differences continue to have the same pattern, we would actually describe this data as exponential. And when you learned about exponential functions in Algebra 1, you probably looked and said, well, is it more like a pattern where there's multiplication involved or division? And we'd say, well, each of these entries, if we multiplied them by 2, we would keep getting the next number. And so that's one of the ways we looked at finding out if a function was exponential. So exponential functions you've looked at for a while. As I said, back in Algebra 1, it was a long time ago. But it's best to compare them to what we've already learned. So linear functions model situations when a number is repeatedly added or subtracted each time to create a pattern. And we're used to those, like 1, 4, 7, 10. We keep adding 3. So we take the number that we keep adding, 3, we multiply it by x, how many times we've added it, and we start at the first number, which in this pattern happened to be 1. And so that starting value, that y-intercept that we came to call it, was added on to the end. And now we're going to look at examples where we multiply or divide. So here in our example that we started with, each time we multiply or divide by 2 to get the next term, specifically we're multiplying by 2 to get this next term. And patterns, functions that follow this kind of pattern are called exponential functions. The parent exponential function is f of x equals, now I'm going to write it as a times b to the x value, a times b to the x. And I know later I don't actually have it written as a times b to the x. I just have it as b to the x. But the base of this function, regardless of how you write it, the base is b, and it represents a constant, so that's really going to be a number, and the exponent suddenly becomes the independent variable. So we're no longer plugging in a number that we're going to raise to a power, like we did with polynomials. Instead, we're going to plug in values as the powers. Now, it's really kind of important to keep in mind that all of these exponential functions, regardless if we write them a times b to the x or just b to the x, b has to be greater than 0, it has to be positive, and it can't equal 1. So nothing's going to grow exponentially if you just keep multiplying it by 1 each time, and that's why it can't equal 1. All right, so we've worked before with, evaluating them, just kind of harkening back to Algebra 1 again. So basically the way you start usually looking at these is you plug them into a table of values and you plug in different exponents. It's important to keep in mind that, okay, if we have a negative exponent, our function that we're looking at right here, 2 to the x, if we raise that to the negative exponent, right, it's going to be 2 to the negative 2. Because we're plugging negative 2 into that exponent right there. And what that really means is 1 over 2 squared. So what is 1 over 2 squared? It's really 1/4. All right, and if we raise it to the negative 1, 2 to the negative 1 will really be 1 over 2, so 1/2. And 1 2 to the 0 power. Any number to the 0 power we should remember is 1. Plug in 1, so 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. So this one is nice. We can get kind of a lot of examples here. So this is 1 right here. So when I plugged in -2, I got back 1/4. So that would be like right there. And when I plugged in -1, I got back 1/2. And when I plugged in 0, 1. 1 gave me 2. 2 gave me 4. We'll see really quickly. It gets a lot higher, right? So these are our points. So it looks like the domain, it looks like we're plugging in all different, positive and negative numbers. Technically, we could plug in some fractions because we know that those are just examples of roots. So it does look like our domain seems to be all real numbers. And our range, though, right, well, it kind of looks like if we kept tapering off, even if we had 2 to the -3, it wouldn't become 0. It would just kind of get smaller and smaller. So the range does look as though it is going to stay above 0. Right, I'm trying to connect these dots with a smooth curve. And that is true. So the range actually will be not a bracket, as I almost wrote, but it will become 0 to infinity. So will it reach the x-axis? The answer to that is no. No, it will not reach the x-axis. And so we know that if something gets closer and closer to a value but doesn't actually reach it, which is what would happen here if we kept adding more negative numbers, it must have some kind of an asymptote. And specifically, this is going to be a horizontal asymptote, which is a line that a graph function approaches as the value of x gets small or large. In this case, as the value of x gets very large as a negative number. So we're going to have this horizontal asymptote on the y-axis, on the x-axis for 0. All right, so this graph that we just looked at is a specific kind of graph. It's called a growth graph, and the reason why it's a growth graph is because as we go to the right, as x gets bigger, our function is increasing. So a function of this form, a times b to the x, is going to be an exponential growth function. As long as that b value, that base of that exponent, is bigger than 1, and it increases as x increases. But if b was somehow less than 1, but we know it has to be bigger than 0, it can't be negative. So if it was bigger than 0 but less than 1, it's going to become an exponential decay function. You might have heard about these in science. You guys might use these same words. So it's an exponential decay function because as x increases, it decreases. The way I like to think about it. Some people also say that it increases as x decreases, which really does mean the same thing, but it's, in my opinion, a little strange to look at it that way. All right, so knowing whether or not something is going to be a growth or decay function does help us with the graph, so it's good to kind of analyze that. So if I'm looking at this value right here, 1.5 to the x, the base is the number that has the exponent, so our base is 1.5. Above, it tells me that because it's bigger than 1, it's going to grow, and that will help me make my table of values. Now, I'm going to use a calculator to help me make my table of values just so that we can kind of time save a little bit here. So I'm going to put in 1.5 to the x in my graph. I'm going to look at second table. And hopefully it's set up correctly, which it is. I think it's always important to have that y-intercept there. So honestly, if I'm plugging in 0, that one's really easy to do by hand, right? So if I'm plugging in 0, anything to the 0 power is going to equal 1. I'm going to put a number on the left, so a negative number, so -1 would be 2/3. 2/3. I think that's almost easier to do with the exponents. And then now if I go ahead and I plug in a number like 1, obviously I'm going to get back 1.5. And if I plug in a number like 2, I'm going to get back 2.25. 2.25. So I'm going to go ahead and graph these, and knowing that that 1.5 makes it a growth function is going to hopefully help me realize whether or not I am doing a good job in terms of, I'm kind of going up a scale too, in terms of getting the right points here. 1.5, I'm kind of coming up with my own scale. 2 would be 2.25, something like that. Right, but it's really important that I try to make sure that I don't draw it just going straight down, because it doesn't go straight down, and it's going to have that horizontal asymptote here at 0. And in fact, unless we go ahead and move this exponential graph up or down, it's always going to have that horizontal asymptote of 0. All right, here we've got another exponential. 30 is not the base. 30 is actually the y-intercept. And the reason it's the y-intercept is because if we went ahead and plugged in 0 to our exponent, this whole term is going to turn to 1. And so whatever number is here just gets multiplied by 1 and just becomes the y-intercept. So right there, 0, 30, that's the y-intercept. Now the base is 0.8 or 4/5. And since this is a number that is less than 1, it's going to hint to me that we are going to decay. So it's kind of important to know that. So my graph should be coming down to the right. So I'm going to go ahead and plug that in. 30 times 0.8 to the value of x. And if I look at that in terms of the table, these values are not the best. I'll admit that. So when we go ahead and we plot them, if I look at negative, at 0, 30, negative 2 would give me something up here, 30, 46 something. So kind of up there. And then maybe I'm going to give myself this value at 4 being like 12 something. The problem is it kind of looks a little bit linear here. But if we went a little bit further and got some values out here, like maybe at 10 it's 3 point something. Over here at 10, 3 point something. Maybe like right here, you can kind of see that it's going to start to curve. Right, and I'm going to put the other arrow on the other end. All right, so if you want to try and practice that again, go ahead. It's always a good idea to predict if it's going to grow or decay. All right, so basically, this generalized formula is called the growth or decay model. So we can model growth or decay by a constant percent. The constant percent is really important. If it grows and decays at different amounts, this model won't work. So we can model growth or decay by a constant percent of increase, either or decrease, using this formula. And the formula says that, okay, this final amount, the amount after some time has passed, equals A, the initial amount, times, in parentheses, you either are going to 1 plus the rate you're adding to it, or 1 minus the rate, depending on if you're growing or decreasing, raised to T, the number of time periods. And this doesn't always have to be the same. T could represent days or weeks or hours or minutes, depending on what we're working with. Okay, so in the formula, the base of the exponential expression can either be 1 plus r, and if it is, that would be called the growth factor, or it could be 1 minus r, and that would be called the decay factor. So we're going to read some problems, and we're going to write an exponential model. And once we write the exponential model, we're going to go ahead and graph it. I'm going to use a calculator to do this, and we're going to answer this question, right? So Tony purchased a rare 1959 guitar in the year 2000 for $12,000. So if he purchased it in the year 2000 for $12,000, this is our A, our initial amount. Experts estimate that the value will increase, right? So increase implies that our growth factor is going to be a growth factor. So we're going to add 1 to the rate by 14% per year. So our time is in years. And we're going to use a graph to find when it's going to equal this value, $60,000. So the first thing we're going to do is we are going to model this. So A of t, this is my growth model, is going to equal my initial amount, 12,000, times 1 plus the rate, 0.14, to the exponent of x, or t, or whatever it is you would like it to be. All right, so this is my exponential model. Now what we are trying to figure out right now is we are going to try to solve the problem, when does this equal $60,000? Now we haven't learned enough yet to solve this by hand, and we will. That's the whole point of this unit, so don't worry about that right now. But what we're going to do right now is we're going to graph it. So this graph over here, I'm going to use kind of just to roughly sketch what is going on my paper. On my calculator. So I'm going to type in the growth model, 12,000. I don't know why I put a comma. Sorry, 12,000. 12,000 times 1 plus 0.14, which obviously I can write as 1.14. That's totally fine. To the power of x. And I'm going to enter that. And then the next one, right, so I'm going to enter this as y1, and then I'm going to enter my 60,000 as y2. And what we want to do is we want to find out when the two meet. Now, if we graph it in our standard window, we will probably see nothing. And that's because we have to kind of do a little thought around this, right? This guy's y-intercept, we just said that the initial amount was 12,000. Here I'm looking at a screen from -10 to 10, -10 to 10. I can't see 12,000 on there. So I do need to change my window, right? So x represents time. No way I need to see that much negative time. Maybe I want to see -10. That's fine. -1, I'm sorry. And how long do I think it's going to take? I don't know. Maybe 15 years. This is a total guess. Just, it's not probably going to take 100 years for it to equal $60,000. It wouldn't be a good investment if it was. But y min, this is kind of more important. Sure, I can start at -10. That's fine. But y max, I mean, if it starts at $12,000 and it's going up to $60,000, I need to see a lot of y. So maybe I'm going to give 70. Ooh, I think I did too many. 7, 0, 1, 2, 3. 70,000. And I'm not going to go up one at a time if I'm looking at 70,000 units. So I think maybe I'm going to go up 10,000 at a time. All right, so that should help me see my graph. Which, yep, I can right about now. So I'm just going to really roughly sketch it over here, right? So I look like I'm seeing something. Obviously, I don't have the right scale, but I'm seeing something go up like this. And then this line across here, whoa, that's supposed to be a horizontal line, but that's representing that 60,000 that we put into Y2, right? We put this guy into Y2. So now we're going to find out where do they meet, and our calculator can do that for us. We're going to hit second calc. We're going to find their intersection. That's option number 5. If we only have 2 equations, it's going to be okay. We just hit enter first curve, enter second curve. And then if we want to get a little bit closer, we can. That's a good idea if they intersect in multiple locations. You can also enter a guess. And it's going to be 12.283. 12.283. So they intersect at 12 at the point 12.283, comma, 60,000. All right, so how does this answer our question? It says experts estimate basically when will it equal this? So 12.283 years after 2000. So I could write my answer something like in the year 2012. Now I could get very specific, and we can talk about this in class. I could find out what 0.283 of the year is. It's a little over a quarter of the year, so I could be more specific and say in April, and we can talk about how to turn that unit into a more specific date if we had to. All right, here's the same problem. Here's another problem that you can try if you would like to. Just go ahead and pause if you want to give this one a shot. I'm going to do one example of exponential decay in the same idea. So we have the value of a truck bought for $28,000 decreases. That word decreases makes you realize that it should be decay. So this is going to be decay. And we want to write our exponential model. So hopefully we can say by now the amount after some time has passed is the original value, 28,000, times 1 minus 9.5%. It's not 0.95, it's 0.095. That's really important to remember that. To the exponent of x or t, whatever variable. Actually, I should use t. The reason I should use t is because I said the amount after some time, and I referred to time as a t in this original problem. And so we're going to want to figure out when this value falls below $5,000. If anyone has ever tried to price cars, this is very much a question that people are always trying to figure out. And how much cars are actually worth. So this is the problem that we're trying to solve. We're going to use our calculator again. It's a decay model this time. Oh, that's not what I want. 28, 1, 2, 3 times, and then 1 minus 0.095 to the value of x. And that's going to be 5,000. We may want to go ahead and adjust our window again, thinking about this value, right? So -1 to 15, I'll keep that because I'm not sure yet. My minimum value, -10, but I don't need to go up to 70,000 because the price of the car when we start talking about it is 28,000. So maybe I would look from 30,000 down to -10. And I probably don't need to go 10,000 at a time. I can if I want to. I could also just go maybe like 5,000. I like to think if I was going to graph it on paper, what was a scale that I would feel good about. So I'd feel good going by 5,000s. All right, so this happened right here. I don't see the intersection, but I can imagine it's off to my right a little bit more. So I'm going to go back to my window and I'm going to adjust it. So maybe I'll go an additional 10 years. It's probably maybe more than I need, but it should guarantee I'm going to see where they intersect. There you go. So on my paper over here, I'm looking at a graph. It's kind of like this. Really rough sketch over here because we're not doing exact graphing like we were at the beginning. So we're going to second calc. We're going to find our intersection point. 2 enters as long as you only have 2 curves in there. I can move my cursor a little bit more. And it looks like 17.258, 5,000. So parentheses 17.258, 5,000. So when will the value fall below 5,000? So it will fall 17.258 years after the year that it was bought. So since we weren't exactly told when the year it was bought in, so between 12 and 13 years after the year in which it was bought. All right, so I have one more problem for you to go ahead and try yourself. Just make sure you're comfortable with the calculator. That's going to be required, and we will do some more with this in class.